Hello everybody and welcome to your video notes. This video's objective is, by the end of this, you should be able to say confidently, I can make LOL and LOL diagram for an open or closed system. My name is Mr. Basil and let's get to it. So, I'm going to review some things that we've already covered in previous videos just to make sure that we have a good foundation before we move on to the more complicated problems that involve an open system. So remember that moving is when you have kinetic energy. So if something's moving faster, it has more kinetic energy. If it's moving slower, less kinetic energy. And not moving at all, zero kinetic energy. If it's above the reference point, that's when you have gravitational potential energy, or what we're just going to call potential energy. And if something is stretched or compressed, it has elastic potential energy, or what we're just going to call elastic energy. So we're going to drop the potential energy there. And then the reference point is always going to be the lowest point in the scenario. You'll see examples of that in the lesson for today. And the system is what we were looking at, aka the house, in like the house analogy where you have little blocks in the house or outside of the house. An LOL diagram is, oops, see, there you go. LOL diagrams track energy changes in a system. And so the first part shows the initial energy that's in the system. The second L or the second bar graph shows the final energy in the system. And then the O lists the objects that are storing energy within, again, the system. And then the different bars above the different kinds of energy show, what kind of energy is in the system. So this was one of the examples we did. We looked at part A and part B, and for each part we're looking at just like a snapshot of where something's at. Where the car is moving fast, so we had lots of kinetic energy. We said the system was the car and the earth. And then in the end, the car was moving fast above the ground, and so it had kinetic and potential energy. And remember, the reference point being the lowest point, no potential energy at the beginning. The number of bars does not matter, just as long as the conservation of energy is conserved, like the right amount of boxes are before and after, and then make sure that you have the right kinds of energy. You could have had 2 bars, in kinetic, and then 1 bar in each. That would have been fine. And then you have your qualitative equations that you're supposed to do, which again, they just match up with where each of the different bars are, the different kinds of energy that are present before and after the scenario. So here we had a system that was the car, earth, and spring. We're going to look at variations of that one here in just a second. So I want to revisit that one as well. So in the beginning, since the spring is in the system, it's full, and the spring is being squished, we have elastic energy. And then in the end, it's just kinetic energy because the spring is, not being compressed anymore. And so all of the energy went from the elastic account into the kinetic account because the spring caused the shopping cart to move. All right. And then our qualitative equation, elastic energy equals kinetic energy. All right, so now, let's move me down here. So work is what's going to cause energy to enter or leave a system. It happens when there's a force that is external that's applied to the system. You can pause this as you need to, so that way you can copy this. You need to copy this down into your notes. But pause as needed if I'm going too fast for you. This can be for anything that is outside of the system. And friction is an example of something that's always going to be an external force. And again, an open system is when energy enters or leaves the system. And I'll show you how you're going to represent that here in an example coming up. And then a closed system is when all energy stays in the system. So all the examples that I've showed you so far, two examples so far, yeah, those are all examples of closed systems. And now I'm going to show you examples of open systems. Said for now everything should be a closed system. That was the before ones, but now let's look at handling open systems. So here we go. In your notes, I want you to draw this again and draw this again. And this time, I want you to say that there is friction. Make a note off to the side somewhere that the system is the cart, spring, and earth, and that there is now friction. We have to deal with that. So remember, since friction is an external force, there's going to be some transfer of energy. The beginning part is still going to be the same. We still have the spring in the system, So we have 1, 2, 3, 4, 5 bars in the elastic account, and 0 in the potential, and 0 in the kinetic. And the reason, excuse me, swallowed wrong. So the reason why there's 0 in potential again is because it's at the lowest point it's going to be at. And the reason why there's 0 kinetic at the beginning is because it's not moving. All right, so now we have to figure out, okay, well, what's going to happen if there's friction? Well, we know that if there's friction, that's going to cause it to move slower, right? So in the end, it's going to have less kinetic energy because it's moving slower. So I decided to show that by only drawing 4 boxes or 4 blocks of energy in the kinetic account. And you'll notice in the center, and I'll stop moving my mouse so that way that black bar goes away. I have 1 bar or 1 box, and I have an arrow next to that showing it going out of the system. And the reason why I'm doing that is because friction caused energy to leave the system. And so, it did that by doing some work on the system. So the way I'm going to show that is just as I have it shown here, where I've got the elastic energy minus some work, and that work is due to friction, that equals the kinetic energy in the end. And the way I can make sure that that makes sense is I've got 5 here minus 1 equals 4. So I could imagine like this part's 5 minus the 1 box that I drew there equals 4. And so that's how we're going to show energy leaving the system. And we're going to do the same thing if energy enters the system, except we would just have the arrow pointing back in. Okay, so friction is always going to cause something to leave. Now let's do another example where something is a little bit different. So we're going to do this scenario again. And again, I would say maybe you could draw this again, or you can say same as before, but no friction, but the system is now not including the spring. So remember, the stuff that goes in our bar chart can only be for the system. And so in the beginning, there's going to be no energy in the system because the system does not have the spring in it. Sure, the spring does have the elastic energy, but this bar chart is only for the system. And now we're saying that there's no spring in the system. So in the end, we know that it still ends up with a bunch of kinetic energy, right? And if we make it match how we had it before, we're going to put 5 bars there. Now the question is, right now, how do I make this work? Because right now I have 0 equals 5, but that can't be possible, right? So instead, what we're going to do, and again, pause is needed so that way you can jot this down in your notes, we're going to have 5 bars of energy going into the system. And that's the way I decided to, that's why I drew the arrow going into the system this time. I've got 1, 2, 3, 4, 5 bars going in. And then for my qualitative equation, I don't have any energy in the beginning. So all of my equation is just going to be is that work equals the kinetic energy for part B. And if I plug in the numbers for that, I've got 5, and that equals 5. All right. Let's do a few more examples because I have a feeling that maybe this is feeling a little weird about it, and that's okay. So let's do a few more examples. Let's do a completely new scenario this time. So again, I want you to jot this down in your notes. You got a hill, you've got a ball that's moving, and that's part A, and then part B. Well, here I have this here. So point A, a ball is rolling down a hill slowly. Then point B, the ball is at the bottom of the hill moving very fast. The system is the ball and the earth. Now, again, you want to draw your LOL diagram, and we're going to put the ball and earth in our system. You'll notice that I have a question here that says, where should our reference point go? Because it's on the ground, so some students might say, oh, it's on the ground, so there's no potential energy. But in reality, the lowest point is going to be right here. When the ball gets to the bottom of the hill, that's the lowest point. So our reference point, you should draw this in on your picture. And again, pause is needed, but draw this in and say that your reference point is a dashed line right there. Okay? All right. Now, you'll notice that I did 4 bars of energy at the beginning. Let me move myself back up here. There we go. So I have 4 bars of energy at the beginning, and that's in the potential account, and then 1 bar of energy in the kinetic account. I chose to do that because it has a lot of potential energy because it's really high above that dashed line that I put for the reference point. And it's moving slowly, so it has a small amount of kinetic energy. If you chose to do 3 bars in 1 bar or 5 bars in 1 bar, that's fine. You just need to have a small amount of kinetic energy and a lot of potential energy in this one. Now in the end, notice that I made it all kinetic because when it gets to the bottom of the hill, it's going to be moving a lot faster and all the energy has to stay in the system. There's no friction, there's no external forces, so I would have 1, 2, 3, 4, 5 bars here and have 5 bars on over here, and then I can represent that with my equation. The potential energy for part A plus the kinetic energy for part A equals the kinetic energy for part B, and altogether the 4 plus 1, that equals 5. Okay, so this was a closed system. Let's see what this would look like if it were an open system. So let's do this one now. I want you to try to maybe pause this and try to do this one on your own. See what you can do. I'm gonna wait for a little bit to give you time to pause and come back. And now I'm gonna say share the answer. Okay, so here we go. So it's the same scenario as before, but this time we have friction. So the reference point is gonna go in the same spot. And the beginning is gonna be the same as well, because there's nothing different about the beginning this time. And now for part B, that's where things are going to be different. We know that friction is going to cause this ball to move slower. So before I had 5 bars of energy, now I have 4 bars of energy here. And notice how I have the 1 bar that's leaving the system. So I made a note on this one just to kind of drive that point home that this is because of work. The work is coming from friction. And so we're going to want to represent that in our overall equation as well. So I've got my potential energy for part A plus my kinetic energy for part A minus the work from friction. So it's good to make a little note of like, where's that work coming from? And that equals our kinetic energy for part B. It seems like a lot's going on, and there is. But if we just break it down step by step, it's actually not so bad. So 4 plus 1 minus 1 equals 4. So not so bad math, but it's good to break it down step by step. All right, let's do one more example. All right, so now this one's gonna be a little bit more different. Oops, that one's just floating there. Well, you'll see why that's there in a moment. Now what I want you to do is I want you to pause, read through the problem, see if you can do it on your own. Note the things that are different, specifically that the ball's at rest here. So that's going to change something. And then it says that a person kicks the ball. Interesting. So see if you can come up with this one on your own. Again, pause, work through it, and I'm going to go over the answer here in 3, 2, 1, rock and roll. Here we go. So here's how I decided to do this one. Where should the reference point go? Same as before, the lowest point that the ball's going to be at. Then over here, I decided to do 1, 2, 3, 4 bars of potential energy because it's above the ground. And I decided not to do any kinetic energy because it says the ball is at rest. Now it says, then a person kicks the ball. Person is not part of the system. They're applying a force to the system. So we're going to have some energy go into the system. You could have as much energy go into the system as you want. You could have started with 1 bar in potential. Doesn't matter to me. And you could have had 6 bars go in right here. I just chose to do it this way. In the end, what matters is that the total amount of bars or boxes add up to the overall to make sure that energy is neither created or destroyed. So in the end here, I've got 1, 2, 3, 4. I said 1 came in, and I said work from the person. And so I have 1, 2, 3, 4, 5 total that I have to represent on the right. And at the end, I have 1, 2, 3, 4, 5 there. Awesome. It would be incorrect to have potential energy at the end or elastic energy because those wouldn't apply in that for this situation. And then in the end, this is what my final answer would be. So the potential energy of part A plus the work from the person. And again, it's good to make note of where that work comes from. And then that equals kinetic energy for part B. All right, that's it. That's all the examples I have for this. If you want to see more examples, check the description of this YouTube video, and I have some more worked examples, 2 more in fact, if you want to see more problems from me. All right, thanks for watching, everybody, and have a good day.